So thank you ever so much for the invitation to speak here today. It's an absolute honor to be at KAIST. So thank you very much to the organizers of the conference for inviting me. Thank you, Julia. That was amazing, absolutely amazing always to listen to your perspectives on the Anthropocene. And always, as ever, I realize how little I have read and so much to understand about the Anthropocene, even though I seem to be spending every day, every waking hour for the last few years working on this will o' the wisp, the Anthropocene that we hope to pin down, and that's essentially what I'm going to be going through today. I'm going to be talking about defining a golden spike for the stratigraphic Anthropocene. So I'd like to briefly introduce what the Anthropocene Working Group has been doing over the last few years in collaboration with the Haus der Kultur und der Welt and the Max Planck Institute for the History of Science, both of which are in Berlin, and many of you know their work. This will be a summary of recent research by the Anthropocene Working Group and the collaborating scientists around the world that we're working towards formalizing the proposed Anthropocene epoch. I'll also mention how we have been exploring some of the wider cultural and historical perspectives of the Anthropocene. So this is the Anthropocene we consider suitable for formalizing as a new geological time unit. This lower graph below, the greenhouse gases there in purple and orange, they show the concentration of greenhouse gases, carbon dioxide in purple and methane in orange, from the late Pleistocene through the Holocene to present, as recorded by polar ice cores and atmospheric monitoring. The panel to the right shows these concentrations at the same vertical scale as that bottom one there, but focused only on the last 300 years and its connection, its direct connection of those increased concentrations as a result of fossil fuel production and the combustion of those CO2 emissions. It is this supercharging of the Earth system by our activities that has moved our interglacial conditions outside of the norm, outside of the Holocene, and it's a planetary transformation powered by unprecedented fossil fuel combustion that accelerated from the mid-20th century. So clearly, as Julia said, and as we all know, human activity affecting geological processes did not just start in the mid-20th century. The evidence of that, as Julia again said, stretches way back into the Pleistocene, and you can see that in that bottom left-hand graph there, that the previous epoch from the Pleistocene into the Holocene, the change there in those atmospheric concentrations is measurable and recordable, but it's this very, very recent planetary scale change due to human activity, which is sufficient to be recognized, we believe, as a new chronostratigraphic time unit. So this was a last minute slide, but I thought, even though I'm talking today about some of the detailed aspects of chronostratigraphy, I'm talking here now, but I'm also really excited to be here to learn and find out more about the Asian Anthropocene and about these, globally, these unique regional and local forces that have created a global Anthropocene. Just one moment. So, like all good students, not knowing where to start, I was quick to start reading Wikipedia. And if you type in anything about the history of South Korea, these sort of curves come up pretty quickly, showing this incredible transformation of the economy. And I'm not a historian or an economist, but I know there are limits to what a GDP plot like this tells you about a country. But it's this plot of economic change and the relationship with the Anthropocene Working Group is not a coincidence. It's the processes and order of magnitude change that created this regional change in the Republic of Korea are those that contributed to the global changes of the proposed epoch. It's certainly not Republic of Korea's contribution only. It's a global contribution. So you see these changes all around the world. So Julia briefly mentioned this, but there's a slight formatting error, but I hope this slide goes some way to explain how a small group of scientists have ended up with the responsibility of potentially taking us out of Holocene. It's a small task groups, as we are, the Anthropocene Working Group, have always been put together by sub-commissions in the International Commission of Stratigraphy to investigate new or reappraise existing stratigraphic boundaries and names. So just at the bottom there, this is where we sit in our chain of bureaucracy of organizations, and this is sort of like how chronostratigraphic time is defined, going all the way from the bottom up to the top to the International Union of Geological Sciences. On the right, which is terribly formatted, which I do apologize, but this is a summary of our origin story, and I'll just go through it. Clearly there are other stories that describe the stratigraphy of humans and origins of thought on how we situate ourselves as members of a planet, but this is our timeline. I've even added our own GSSP, but our thought, and this is our sort of stratigraphy of thought that has developed, and it's also the most sort of direct way I can sort of explain how we find ourselves today. So I'm starting at the bottom with Paul Crutzen and his statement about saying we no longer live in the Holocene, but we are now in the Anthropocene. And this was a profound outburst to make, and it really had an impact on the geoscientists and the Earth system scientists in the room at the time in Guadalajara. But it took a while and lots of papers and sort of consideration and thought, and it really took on a massive change, as Julia again said, with the work by Paul Stefan, and this idea of a great acceleration, and it was taken up that if there was this historical change, then it was so profound that it's almost certainly resulted in a stratigraphic change that could be measured, in global stratigraphies. And so in about 2006, there was a meeting of the Stratigraphy Commission of the Geological Society of London, when all this was discussed, and that resulted in a GSA Today paper, when it was actually considered that this could actually be done as a formal geological time unit. And then there was a long period of time when this was sort of worked on. We were very lucky by about 2014, I believe, when HKV got involved, and they sort of supported the AWG work by actually enabling the AWG to physically meet. Up until that point, everything was done by email or sort of small groups of people. Two defining periods of two events happened one in 2016 at the International Geological Congress in Cape Town, when there was a question: should the Anthropocene be treated as a formal time unit defined by GSSP? And we'll come on to GSSPs in a minute. And should the base be the mid-20th century? And this was like a formal vote that was taken by the Anthropocene Working Group. And 2019, those questions were answered by voting, and it was agreed that this should be the official stance of the AWG. So that's what was decided to move on and sort of progress the stratigraphic work. Around that time, again, we were very lucky to actually receive some support from the Haus der Culture and Development, the Max Planck Institute, and we started this program called Evidence and Experiment, where we actually started bringing together for stratigraphic evidence, and actually, we said we were going to do this, and now we're going to do it. And that brings us right up to the present day when we've actually voted, and I'll come on to that in a minute. And we've actually now found a site, and we are now enabled to then progress to the next stage and move our way, our ratification process through these commissions and the International Commission very soon. So here, if I know this is an environmental history conference, and I realise I'm talking about stratigraphy, but this is overall what we're trying to achieve. This is the June 2023 version of the International Chronostratigraphic Chart. There are three things I'd like to just impart here. One is related to the last sentence. This is an ongoing process. This is the June 2023 version. There was a previous version earlier in the year, and this is an ongoing process. GSSPs, you might just be able to see there's little golden spikes running down the right-hand side of each of these columns. GSSPs is a process to try and define chronostratigraphic time from about the 1970s the International Commission of Stratigraphy decided this is the way to go. But this process is a continuous process, as science is always. When new evidence has come about, then these boundaries have been reconsidered and reappraised. The second thing about chronostratigraphy, rather than sort of what you might think about stratigraphy, is that there is no evidence on this graph at all of what the actual material evidence is. These are all boundaries and names of defined geological times to only help correlate the evolution of a planet. There's nothing here about sandstone or mud or volcanic rocks. This is all just like organizational bureaucracy of how to order these time units throughout the evolution of the Earth. The other thing I always think about when you look at this is even though if we do ratify it as an epoch, it will be just the tiniest line on that top left-hand column there. It will just be very thin, but its present here will be a significant statement of the magnitude of change that has occurred. It is quite a thing for a species to change a planet, and it's not something to be congratulated on, but it is a thing, and I think having it defined geologically will help, really emphasize the impact that we have had in the very recent past. Sorry, I've got two computers on the go. Okay, so I mentioned GSSPs, and GSSP is a global boundary stratotype section and point, or colloquially known as a golden spike. So following the rules, and there are a lot of rules of the International Commission of Stratigraphy, boundaries in geological time are marked in the geological record and formalized by the use of these golden spikes, so literally and numerically. And so here's a summary of stratigraphic requirements to determine a GSSP. So they must contain a marker, and we'll come on to markers in a minute, but they define the lower boundary of a unit, and it allows correlation globally, and that is a key point. It's this ability to sort of look at things on a very large scale. They must be defined by a change in physical or chemical or fossil content and should be datable, and so that's independently datable. They must be of adequate thickness, so you can actually go back and reuse material, and they must show continuous sedimentation. And they must also be accessible to research, purely, just as a consequence for, technology changes, precision of analytical materials and equipment change. So it's always a concept of going back at various times and looking at this again. So it's ceremonial and an exercise in geological bookkeeping clearly, but also critical in understanding planetary evolution. In an ever-changing planet, time has at the least been and remains a constant reference for global correlation. I just thought, here is an actual spike. It's not gold. It's usually a bronze thing, but this is one that was inserted into a rock face in Spain, Guadalajara, in the mid-1990s to delineate the base of the Middle Jurassic. These are all good facts to remember from today. 174 plus or minus 0.8 million years. And so that's what golden spikes have traditionally looked like in geology. So if we're determining a chronostratigraphic Anthropocene, we therefore require these stratigraphic markers of environmental change generated and affected by human activity. So listed here in this table are many of the key determinants being measured by the group, scientists within the group, and should be stressed that not all things are measured in all the cores we are using, because the environmental archives that we've used for this project and the variety of environmental archives you find globally, not all markers are recorded the same. But there are many cross-core determinants. We really wanted to make sure that as we were analyzing this data set, that we could look at one determinant and see how it contrasts across all those different archives. So all these techniques, these are very common techniques, and they have a long heritage of being used to measure human impacts. Some more directly and specific to a technological process, others like ecological indicators over there on the right, but they're they're more responsive. Things like algal concentrations in lake waters respond to nutrient inputs, for example. And most of these have been also used to determine defined units of time in the Quaternary. So we're not having to invent any technology to actually measure the Anthropocene. We're using very normal processes and methodologies to measure environmental change. One of the key things is with chronostratigraphy is there's always a requirement for a precise chronology. So we looked for sites with annual, even subannual layers that can also be checked by independent radiometric dating methods. A key set of markers, therefore, the radionuclides from the atmospheric weapons testing that provide an almost globally synchronous marker of the mid-20th century. And this level of chronological precision is pretty unique. I think it is unique in the history of GSSPs to be able to define specific years. Is an astonishing achievement of stratigraphy. So the primary marker we're using is plutonium, and we should never overlook what we consider this as this primary marker. It's incredibly useful, but the use of plutonium as a synchronous chronostratigraphic marker is very much a marker of human history. It's not independent of it. Its first release into the environment came from early tests and use as a weapon of mass destruction. But it was the initiation of a program of high-yield thermonuclear testing, beginning with the 10.4 megaton TNT equivalent Ivy Mike test at Enewetak Atoll in the Pacific Ocean on November 1st, 1952, that nuclear fallout, atmospheric fallout, shifted from being a regional to effectively a global fingerprint of nuclear activities. And it's this fallout that persisted until testing that went underground in 1963-64. And this plot here is just time along the bottom, and in dark is the numbers of atmospheric tests, and the line is the underground tests. And then, and you can see that for a short period of time, atmospheric testing was very much a thing to test your nuclear weapons. It is an extraordinary thing to have done. In hindsight now, I mean, we talk about health and safety in sort of experimental research. I cannot imagine trying to get this through an ethical research committee to sort of, this is, but if you were thinking of how to create a chronostratigraphic marker that would be spread uniformly around the world and be detectable for tens of thousands of years, then this would be the route you would go down. And just in the green lines there, just show the deposition of plutonium in blue and the atmospheric concentration of C14. And so you get this, you see this atmospheric deposition responding very quickly to the numbers of tests. You even see when there was a moratorium in the mid-1960s, and then a peak up to the 1964. And it's this short time window of plutonium deposition that is global, and it's now persistent, and it's relatively easily measured, and is in effect isochronous. But looking at it in more detail, we also know that not all latitudes were equally affected due to sort of global wind patterns and precipitation. There are slight differences, but in terms of like determining something to a year, plutonium really is one of the few anthropogenic markers that allows that. I'm going to just mention another marker here. This is spheroidal carbonaceous particles, to illustrate their use as a key indicator of fossil fuel combustion. But it's also the technique I have been most involved in at UCL in the geography department. These are microscopic spheroidal carbonaceous particles, and they're only about 20 to 30 microns across, but they were incredibly visible in the mid to late 20th century when they were released in their trillions globally by and only by high temperature power generating stations, as pictured there on the top right. That's a power station in Queensland, in Brisbane, in the 1950s. I think we forget how incredibly polluted city atmospheres were from this sort of combustion, this energy production in urban environments. You just don't see it anymore. These graphs of 8 sites that you've been working on from the GSSP project, these show this sort of characteristic form. I forget that I look at these sort of graphs all the time, and I forget to try and explain. But these are graphs. On the vertical axis is time, and so these are sediment cores going into the past, and time has been calculated, and concentrations are running on the x-axis there. And so when you look at SCPs around the world, you see this very characteristic form in these core depth profiles. You see a very low occurrence in the late 19th century as power stations were invented and came online very slowly in sort of certain parts of the world, sooner, more sooner. Then you also see this big increase in the 20th century, and you see this very distinct increase even more in the mid 20th century. And that is the great acceleration, this switching on of huge amounts of, many, many more power stations being turned on, generating electricity for increased demand. And it's that which created this big surge in SCPs that you see in many sites around the world. So some results halfway through a presentation. So I just thought I'd put this in because this is roughly how we work, looking at these sort of different markers. So this is only 2 markers, and just for the 2 I just mentioned. In black is the SCPs, and in the red is the plutonium. And I just put this together to just show how effective plutonium is that allows global correlation of sites of different matrices. So starting from the left, we've got Searsville Lake, we've got Crawford Lake, a marine core from the Baltic Sea. We've got a peat, and we have Sea Hai Long 1, Ma Lake in northeast China there, and we have Beppu Bay. And so this is just comparing these 2 markers. And you can see the black carbonaceous particles have this sort of distinct form, and like in Searsville Lake, it's quite a noisy signal, and they come in at different times, and it reflects the historical turning on and ramping up of different power stations regionally. But when you compare that with the plutonium signal, it's a very distinct signal plutonium has, but it is non-existent up until the late 1940s. And then you see this increase and onset. It starts to increase at a very specific time in the early 1950s, 50, 51, 53. You see this onset. Then you see a peak in around mid 1960s, and then it declines obviously after atmospheric testing finished. And so it's this onset of thermonuclear atmospheric testing that we consider the most practical and synchronous to time the start of the Anthropocene. And I should mention that the actual precise year we are working on is work that's ongoing currently. So site selection to do this has been a 10+ year process to find sites with annually resolved sediment resolution and archivable core material. Each of these sites was volunteered by research groups. There was no money to do this starting. And they have been actively involved in studying these sites often for many years. They are principally from natural, often remote environmental archives, which are really essential to be able to measure environmental change without themselves being disturbed too much and stopping this sort of continuous sedimentation that is required to accurately record historical events. We also investigated a sequence of urban soils in Vienna. We also looked at sediments impounded behind a reservoir constructed in the late 19th century. These sites were considered suitable deposition environments and with a geographic distribution to identify these globally synchronous markers of the Anthropocene. Unfortunately, for a multitude of reasons, mainly very boring, but just a lack of just enabling, we just really needed groups to start very quickly. We were not able to include successions from South America and Africa, but we have sites we have a traditional, well not traditional, we have an ice core from the Antarctic, we have 2 coral sites, we have marine bays, we have lake sites, we have a peat, and we have a Baltic Sea. So I just put this slide on here because just to illustrate the diversity of sedimentary archives. I mean, it's interesting when you say to people, I look at rocks, people will assume we're looking at rocks. We're not looking at rocks, we're looking at sediments. And I'm often asked, what does the Anthropocene look like? Is it a geological reality? And I used images like this to show that these really are products of geology. They are physical archives of past conditions. And we've used traditional sedimentary and ice cores, but also looked at the extraordinary chronological resolution available from coral sites. And the coral is shown here. This is this is a site from Australia, from Flinders Reef, off Queensland. And what you're looking at there is growth banding that corals produce every year as a result of changing water temperatures, and they create a chronology of changing marine conditions, an annual resolution, like tree rings from trees. So this is what the Anthropocene looks like in a sediment sequence. So I'm just going to present summary results from a few of the sites. I've selected 2 of similar archives from North America and Europe, and also 2 from Asia. When I was thinking about this conference, I was thinking it'd be really good to I think that's why I'm here. I'm really keen to see how this looks like. What does the Asian Anthropocene look like, and how does it differ from sites I'm more familiar with in Europe? So the data I'm showing can be found in the current special issue of the Anthropocene Review that documents evidence from all 12 sites, and that's now available. It was published earlier this year. So there's a lot of information, and I am having to skip through it. So this is the first site. This is the Baltic Sea. This core is from the Baltic Sea in Northern Europe, is collected from the East Scotland Basin from 240 meters water depth. It's an astonishing thing to collect sediment cores from 240 meters below the water, but it's routinely done, and you can collect cores very safely and bring them up to the surface for analysis. You're looking at a finely bedded marine silt and clay succession covering the last couple of hundred years. What we see here, and again, I look at this sort of stuff all the time. This is a graph. You can see the cores there. The age and depth is on the left, and coming across here are these various proxies that we measure, these stratigraphic markers, and how they change in concentration over time. What we see here is evidence from around the mid-20th century. The Baltic Sea became much more eutrophic as a consequence of nitrate and phosphates washed in from much of Northern Europe. Along with pesticides, the orange line there is the concentration of DDT in the mud. And the sediments also reflect this also in total organic carbon content, the change in carbon isotopes due to sort of carbon source changes. And you also, rather nicely, you have a visible color change as well, where that yellow line is there. The team from the German Institute, they identified a stratigraphic change in multiple markers occurring around 1956 plus or minus 4. This is one of the sites that the dating resolution was incredible, but it lacked the annual resolution identifiable physical layers that meant you couldn't really point to a very specific year. So there was an error margin there in the dating. The next site here is in Crawford Lake in southern Ontario in Canada. This is a relatively deep lake. It's about 25 meters deep, but it's very small. And due to seasonal water chemistry changes and lake biological activity, sediments at the bottom have been deposited as finely laminated annual layers or varves. Maybe people might have heard of varves. These very exquisite layers that you see microscopically and to the eye. They've been collected using ice wedge corers that preserve the microfabric structure of the sediment. These are very watery sediments, and they require special techniques to extract them. But using freezers and these freeze corers, you pull them out like dirty lollipops, and then you clean them up, and you can actually see the exquisite stratigraphy. What you're seeing here, and again, this plot here is just a summary of some of the markers of the mid-20th century. You can see the graph in the middle is the concentration of these SEPs coming from high temperature combustion. There's a plot there of plutonium showing this increase in around 1950 from atmospheric nuclear weapons testing. And you also see a delta 15 nitrogen isotope record, which is a response to acidification. It's acid rain. You see that in these lakes all across Europe and the world, where you have a change in the nitrogen sources also from fossil fuel combustion. The 1950 layer here is very visible in the core by eye, as well as using the trends in stratigraphic markers. So over to Asia now. This is Sea Hai Long 1 Ma, found in northeast China. I looked on a map last night, and it's only about 500 kilometers north of where we are today. So this is very much one of the best Asian Anthropocene stratigraphic sites I've seen. The lake is only 500 kilometers north of here, and it's a relatively small, again, and deep volcanic crater lake this time, and it contains seasonal annual laminated sediments. And they record very, very precisely the changing lake conditions and the atmospheric materials introduced to this very small catchment. You can see that you're looking at the catchment there. It's a crater. And so materials either fall onto the catchment and washed in very quickly, or they just fall straight onto the lake surface and then sink to the bottom. You're looking here at this graph here from the paper of a summary of data collected by a team of Yongming Han from the Chinese Academy of Sciences, again using an ice wedge corer. And it shows from left to right these anthropogenic markers, including plutonium, radioactive isotope of iodine. There's a range of carbonaceous particles, including radiocarbon measured in soot. And then there's a series of organic compounds, there's lead, and changes in the biodiversity itself of phytoplankton measured by DNA. One thing to note here is the SCP difference. As mentioned earlier, you see a very systematic pattern when you look at Asian SCP records compared to European ones, but you see an increase, this 20th century increase in SCPs is always about a decade later than ones in Northwest Europe as a result of the change in the way the technology sort of moved into Asia slightly later. And then the next Asian site, just to mention here, this is Beppu Bay in Japan. We have Yoshi Saito here, who is involved with this research as well. So please direct questions about Beppu Bay to him rather than me. But this is an exquisite marine site. It's a deep nearshore anoxic basin of the northeast island of Kyushu. The core site is marked there by the arrow there. It's about 70 meters below the surface. And the Japanese team have been working on a series of cores from the bay for many years as part of a very large national funded research project. And they have produced detailed records of industrial contaminants, nutrient inputs, as well as, rather uniquely, a fish scale sediment record, recording the changes in sardine abundance due to changing water temperatures in the fishing industry. There is so much sedimentological information recorded in these cores. I think it's probably one of the most unique sites in this project. So they use multiple cores, and they show how both local, industrial and land use changes are recorded in the offshore marine basin, as well as the globally distributed radionuclides. In fact, the team analyzed over 90 determinants in the cores. And so it is an astonishing stratigraphic record. The final profile here is interesting because they use a statistical technique that illustrates that there isn't just one line of evidence of the Anthropocene. It is cumulative. It's like in a court. It's not just, you never get a criminal with one line of evidence. It's the cumulative evidence that is so distinct from all these sites. So this is a summary from all the 12 sites. Here are just SCPs, plutonium, radiocarbon, and nitrogen isotopes. And I mean, this is a classic example of how do we start to illustrate this huge amount of data and talk about it in a sort of summary way to communicate it. So these are a series of cores. Along the bottom are the dates to where these actual records go all the way down to. And so, like in Ernesto Cave in red there, we've actually got 8,500 year record to compare the mid 20th century for. And so this graph here tries to show that the peaks, you might think we're just looking for when the Anthropocene's, these markers are at their greatest, but that's not what is as critical because these peaks are very asynchronous. And some peaks obviously predate the 1950s and some peaks are much later. And it's really, like that bullet point there, it's these we really need to look at these local regional histories, which is very important to understand. And so this sort of shows this consistent pattern of maximum change, not maximum change, but there's very significant change in all these sites in the mid 1950s. So what we said was going to be apparent, not to sort of put the cart before the horse, but we knew that the stratigraphic record was going to come to this, and it's quite gratifying to see it to fruition. So we're sort of almost there as the Anthropocene Working Group. We produced 12 papers on the sites and a big introduction paper, and they're all now published in the Anthropocene Review. So, I would recommend to read them to get more details about them. We've now also finished voting. We started voting on the sites around November 2022 with 9 sites, and we do have 1 site now selected. And we will be making an announcement, a public announcement on July the 11th, 2023, which is only 2 weeks away. And I really hoped that we would be able to sort of announce that at this conference or beforehand to be able to discuss this very interesting range of sites, and also, the result, shall we say, compared to other sites we look at this week. I should stress, and I always have to stress, that the Anthropocene Working Group will come up with a proposal, but it is not the final result. After 10 years of work with individuals and groups of scientists, we are only creating a proposal that will go to the SQS later this year, and they need to vote on it as well. And that group of scientists, they have to agree with a 60% majority of our proposal. Only then will it then go up to the International Commission of Stratigraphy, and they have to vote on it. And they have to agree by a 60% majority. And if that occurs, then it will move on to the final processes of possible ratification, or a ratification. And that final announcement will occur in the IGS in Korea in 2024. So I really hope to be in Korea again next year with a very positive finish to this. I do also need to mention this work, because alongside all this stratigraphic work, which has been, a pretty straightforward stratigraphic process to try and define a geological time unit, there's been a comprehensive series of lectures, performances, and installations with our team from HKW through 2021, 2022, exploring the relationship between evidence and experiment and knowledge production in the Anthropocene. It has been a genuinely collaborative effort. It's been novel, and there's been this incredible hybrid interaction between the humanities and sciences. It's something I never thought I'd be doing. Interaction is probably too weak a description. I would push that such collaborative work is essential, and it has been profound in how we think. I certainly have changed the way how I think about my work and why we do what we do as scientists. There is not enough of this transdisciplinary research working with rather than against answers from different disciplines. There are not many positives from the global COVID pandemic, but one of them was forced on us by the virus, because it changed how, as scientists, we worked in this collaboration, and we were forced by the conditions of restricted travel and isolated working practices to become not just the observed as some sort of anthropological study, but we also became the producers of artistic and cultural materials. It's not very often that scientists become artists. So I would encourage people to please do take a look at the Anthropocene curriculum website that contains so much material on the Anthropocene already, that has been compiled and curated by colleagues at HKW and the Max Planck Institute for History of Science. So irrespective, I'll finish very soon now. So irrespective of opinions on the reality of a new epoch, this work has nonetheless compiled some of the most detailed stratigraphic evidence of how humans have modified and impacted ecological and sedimentary systems. If all goes well in the next couple of years, there could be a new addition to a geological timescale, and we will find ourselves not in the Holocene anymore. We will have been in the Anthropocene for the last 73, 74 odd years. If we are unsuccessful, however, the chronostratigraphic evidence of a transformative change in the planet over the last 75 years exists. It's in the ground. It's contained in geological deposits globally, and it's not going anywhere. That evidence will continue to be encountered, even if in the future it is called a different name or considered of far lesser or greater significance, depending on how the Anthropocene pans out. So thank you very much to all those people listed here. It's been an enormous collaborative effort. These mentioned here are just for principal scientists. Please do get in touch, read the papers, get in touch, talk to these scientists. They are very nice people to talk to. You know, you shouldn't, I'm not saying like, but you know, it's good to talk about how science relates to humanities and also how we have these conversations. And there are a lot of people willing to talk about this. So thank you very much for listening. I now very much look forward to stopping talking and listening myself for the next few days. Thank you.